So what we're going to be doing is we're taking a look at this thing called common factors. We spent the last 2 units expanding linear factors to get our final answer. We basically worked on FOIL, and now what we're going to be doing is taking this and reversing it. And in order to do that, we need to understand the concept of common factors. Now, a long time ago, you learned about a thing called the GCF. The GCF is the greatest common factor of a set of numbers by expanding each set of numbers as a prime factor. Now, when you hear the term prime factor, I know you look at that and you're like, where did that come from? Here's the concept. If I take a look at, say, a number like 10, I know that 10 is 2 times 5. If you want, you might want to add this specific concept to your jargon file. Any positive number can be written as a product of primes. Now, when I'm talking about positive numbers, I'm talking about any positive whole numbers. We're not talking about decimals and stuff like that. Okay? Now, when you hear the term, a concept called a prime factor, it's this. Literally, a factor that is prime. It sounds ridiculous. Just understand, it's a number, a prime number that literally divides another whole number. That's all you need to understand. Now, let's move on to part 1 of this set. If you understand how to do GCFs by inspection, just skip this section. It'll be about a 3 or 4 minute example, and then you can move on to the second part right away. So now, let's take a look at this. It says find the GCF of each set of numbers. Now, what we're going to do here is we're literally going to create a factor tree for 12 and 8, and then use that to find the matching sets of primes for each. So now let's do that for 12. 12's smallest prime that divides it is 2. So 12 divided by 2 gives us 6, and then 6 can be divided by 2 again. 6 divided by 2 gives us 3. And now we'll do the same for 8 here. Now, you'll notice 12 and 8 are split, and at the end of each factor tree is its prime factorizations. In this case, we could literally say the following. We could say that 12 is equal to 2 times 2 times 3, and 8 is equal to 2 times 2 times 2. Now, when we use our GCF, if you can't do the GCF by inspection, what we do is we do this factor tree, and then we look for all of the matching pairs. So I'm going to highlight that right now. So in the 12, there's a 2 here. And guess what? There's another 2 here. So now what we're going to do is we look for another set of matching parts. In this case, I got a 2, and I got another 2. So in this case, the GCF is literally 2 times 2, because both of them have 2 sets of matching 2s. So in this case, the GCF of 12 and 8 based on our chart is 2 times 2, or you could have looked at your broken down factors of 12 and 8 and matched them like this and just said, okay, the only things that matches are 2 and 2. So 2 times 2 is, well, 4. Now let's move on to our next problem. So when we take a look at 6, 8, and 24, we don't necessarily have to do a tree. All you do is you just write all the prime factorizations of 6, 8, and 24. So we could just start, if you're really good at math, multiplication and division, you just go, well, 6 is just basically 6 divided by 2. Its first prime is 2. So when you do 6 divided by 2, you're left with 3. Okay, we're done. For 8, you can do the same thing again. You can literally do this. Well, 2 divides 8, and then what's left over is 4. So I'm going to divide 4 by 2 again, and then we end up with, yep, that's it, 2 times 2 times 2. Now, the last one here, 24 might be a little bit more difficult, so I might go and say, okay, well, 24 is just 2 times 12. But then I could go and take this again and then write this again as 2 times, well, 12 can be divided by into 2 and 6, and then I could break that down again into 2 times 2. And we're going to replace 6 with 2 and 3. So then what I do is I go and look for the only things that matches. So in this case, I got a 2, I got a 2, and I got a 2. And that's it. In this case, my GCF of 6, 8, and 24 is just 2. And we're done. Now, if you haven't noticed it yet, we have some rather interesting things we can do with prime factorizations. Now, let's take a look at the GCF of things that have the same base raised to different exponents. Let's take a look at this problem here. I could write this as, well, I have 5 cubed. I could write this as 5 times 5 times 5. And then I could have 5 to the 6, which is just 5 times 5 times 5 times 5 times 5. Well, you get it, right? Now, the only things that matches are these 3 5s. This 3 5s is really just 5 cubed. And this other half of this turns into 5 cubed. So the key, this is the note that we're working with. If I wanted to find the GCF of 5 cubed and 5 to the 6, what you do is you literally take the lowest power of the matching exponent for the GCF. So now if I take a look at 5 cubed and 5 to the 6, I could just tell you right away that the GCF of 5 cubed and 5 to the 6 is the same as 5 cubed, because we take the lower power, and 5 cubed is just 125, and we're done. And now, that's a pretty easy topic to understand now. Let's take a look at what happens when instead of having numbers, we have variables. Now, this here says x to the 4 and x to the 7. So if I used the GCF, I need to know the GCF of x to the 4 and x to the 7. Well, just like before, we said the following. We literally said that this was the case. We said we must take the lowest power for our GCF. And we're going to use that in our next problem. No big deal whatsoever. All right. So we literally have us taking the lowest power. We have x to the 4 and x to the 7. The lowest power is x to the 4. And we're done. That is our GCF. The problem that we're going to do is we're going to combine both numbers and variables to get our GCF. So let's go and do that now. All right. So when I look at 3y squared and 9, if I looked at these as factorizations, this would be 3 times y squared, wouldn't it? And 9 could be broken down into the prime factorization of 3 times 3. The only thing that matches in this case is our 3's. So our GCF in this case equals 3. So the key idea here is to just match the prime numbers for the coefficients and then match the variables lowest power for the variables. That's it. Let's go and take a look at this next problem here to the right. So let's move on to the next problem. So the next problem is we're trying to find the GCF of these two equations. They're actually terms. So what we're trying to find is the GCF of 21 c squared d to the 4 and 28 c cubed d to the 5th. Now, if I did this by inspection, the greatest number that divides the coefficients in this are basically 7 for the coefficients, because 7 both divides 21 and 28. So we're just going to put that down for part of our GCF. Now, when we look at our variables that are common to both, you'll notice that the lowest power between both of these equations is literally, for c, it's c squared, and for d, its lowest power is 4. So our final answer is c squared d to the 4. So the GCF of these two sets of numbers just breaks down to that. Done. And now let's move on to our next problems.